construction from 2x1 softwood and chipboard was described. As it's lowered into position, the track can be seen on its elevated bed. In this issue of Railscale, it will be shown how the elevation was achieved, the track was laid, and the basic outline of the scenery prepared. We found the Super N flexible track could be curved easily, but the nature of its manufacture results in it being stiff enough to hold its shape once preformed, with the exception of the ends, which have a powerful tendency to straighten. These characteristics were used to advantage. All the curves were set out by eye, using the track lengths themselves as templates. These were used to transfer the desired curves to the plywood used for the track bases. We cut the 5mm ply to form the track bed with a jigsaw, taking the necessary precautions for safety. The width of the plywood base depends on various factors. On embankments and viaducts, the base must be accurately produced, whereas in the cuttings the width is not too critical. If the Peco points are laid as supplied, an over-width formation will be necessary to the dimensions recommended by Peco. The track bed was elevated on 5mm ply supports, the parts being glued and pinned with Peco track pins. Strength is only achieved once the glue has set. The pins merely locate the part while the glue sets. We tried softwood with the grain both horizontal and vertical, and heights carefully calculated in order to produce even gradients on curves. It didn't work, and we had to break joints or cut through supports to take out irregularities. We'd recommend retrospectively using the 5mm ply throughout, with the exception of large level areas such as the station and yard. The better the track bed, the better the track laying will be. So we took care to sand the track base to a smooth surface, but did not, unfortunately, avoid a sudden change of gradient on one part of the track bed. This large level area is to become an industrial scene with associated industrial buildings, and will probably feature private sidings and a stone quarry. It's set at the end of the right-hand baseboard.
I'm going to have to apply it to the cork as well.
Cork with PVA applied to one surface and the track base was laid on the track base. The pair of long radius points forming a facing crossover are placed on the cork base. We use Peco Super N for the plain track, but this type was not available for the point and crossing work, not yet having been released. Switches are to be operated by simple point motors, and these are large relative to 2mm scenery, making location difficult, particularly under single-line embankments. Locate the position of the operating hole by putting the switches into mid-position. We found a pilot hole to be essential, as the cork causes the larger drills to wander erratically. Check the hole is in the correct position. Note that an elongated hole will be less obtrusive than a large round hole, as suggested in the instructions. The pilot hole was drilled using a rechargeable electric mini drill that with a circular saw blade easily cuts the rail in situ, a useful addition to the toolbox. The point motor is not readily fitted to the underside of the baseboard, being primarily designed to be above board with a 4mm scale system of trackwork. The baseboard was cut away to get access to fit, wire and maintain the motor. On embankments, there's only just room to screw the motor into position using screws and washers. The hole in the baseboard needs to be as large as possible, but remember that the strength of the board could be jeopardized by too large a hole. Ease of access for wiring and maintenance will be appreciated later, although with hinged baseboards, not all work need be carried on upside down. At least that's the theory. The switches and plain track were laid on a generous bed of PVA and pinned, the intention being to remove the pins once the track work is ballasted. A strong concretion of ballast and PVA is the means of holding the track in position once the track pins are removed. Until the ballast is laid, the track work can be lifted should it be necessary, as the PVA does not adhere to the plastic positively. The central lugs of the point motors are removed and the outer lugs bent to provide a fixing with screws and washers. A test of the point motor operation for clearances shows the operating arm protruding above the point tie bar. This is trimmed to height before final fixing. Finally, the screw and washer is shown being screwed in. On the left is the new Peco Super N track that has a double foot. The lower of the two holds the rail in the track base. On the right, the old pattern with the high rail can be seen. The Super N was used for plain track, but the points are to the old standard as shown on the right. The Super N plain track is not entirely compatible with the older type. The rail height is lower, and therefore the relative position of the sleepers varies. Laid directly against the switches, it's lower, but with rail joiners, it becomes higher. A ramp of plastic card was used to bring the plain track up to the switches. It would probably be better to lay the plain track on a separate cork base to that of the switches, but we found this out too late. We found that the rails of switches and plain track could be moved to even up gaps at joints by gripping the rail with end cutters that were tapped with a light hammer. We also found that it's possible to deform the rail joiners by tapping the railhead with a hammer to even up the rail surfaces. This may affect the electrical conductivity of the rail joint if you're relying on them for electrical contacts. A crossover is seen here, plus other track work laid in the manner previously described. The large access holes can be seen in the baseboard. The area to the left is the beginning of the station yard, with a private branch to the quarry and abandoned branch leading off in the centre. Behind, the high-level main line sweeps over the site of the proposed viaduct.